In this video, we are gonna choose a convergence test to check for the convergence of a series. And this is a page from your textbook that contains all the convergence tests that we talked about in this class. So geometric series, how they look like, what is the condition of convergence, what is the condition of divergence, and comments like calculating the formula for the sum of infinite terms of a series, of a power series. Divergence test, which is the very first test that we talked about when we talked about tests of convergence, we don't have a condition of convergence. So with this test, we do not draw a conclusion if the series converges, but we can find out if it diverges. The integral test, where we look at the shape of the series or a sub k term, and we create a function like that, and we calculate the integral from whatever endpoint we have for the series, so in this case from 1 to infinity. So we end up with an improper integral, and it tells us if the integral if the integral converges, then the series converges. If the integral diverges, the series diverges. The p series, where if p is greater than 1, the series converges. If p is less than or equal to 1, it diverges. The type of the series, the root test, the ratio test, the comparison test, linear comparison test, alternating series test, and absolute convergence. All these have their specific videos, but we are just going to solve a few problems randomly, where we'll decide which series to use, which convergence test to use. So the strategies: you should always start by applying the divergence test, because that's the easiest, the fastest one to decide if your test diverges. Then you should look at the integral test, or maybe ratio test, root test, comparison test, depending on the type of series you have. But a very important advice: convergence tests are mastered through practice. So you have to solve many problems using each of these tests. And here I have a bunch of problems that are from your text that you can solve. It says applying convergence test, and then look from 11 to 50. We have different types, and I would advise you to look over them and just go over each of them and say, what kind of test am I going to use for my problem? For example, if we look at 11, just a quick look, I would use divergence test, and for this problem I would use root test. For this one I would use maybe integral test, or maybe integral test. For this one I would use again divergence test. For this one I would use ratio test, and so on. So try and see what kind of method you would use, and then just solve as many as you can. So I have 2 pages of that, and I actually selected a few problems that I wanted to go over. So let's begin. Example 1. So I want to check if this series converges or diverges. Sum as k goes equals 1 to infinity, negative 1 to k, times 2 plus 2 over k squared, everything to the k. So I'm gonna try and use root test. Sometimes you try a test and it doesn't work and you have to choose another one. But here I will try to use root test. So basically a sub k is the term right after the summation sign. So rho equals limit as k is approaching infinity of k root of absolute value of negative 1 to the k times 2 plus 2 over k squared, everything to the k. So limit as k is approaching infinity, this term here is going to be 1. So now k root of 2 plus 2 over k squared. This quantity is positive, so I don't need to put absolute value sign anymore, to the k. These two cancel, and we end up with the limit as k is approaching infinity of 2 plus 2 over k squared. This term is approaching 0, so it's equal to 2. Because it's equal to 2, that is greater than 1, so our series diverges by a root test. So let's write to be really clear which test we used. Let's do another example. Sum as k equals 1 to 3 to infinity of 2 over k squared minus k minus 2. So taking a look at this one, if we do divergence test, we get 2 over infinity, which is 0, so the test it's inconclusive. So let's try another one. Let's try integral test. So I'm thinking let's try integral test. So that means we are going to use this, and we're going to create our integral to be integral from 3 to infinity, right, from 3, because it starts with 3 and goes to infinity, of 2 over x squared minus x minus 2 dx. So we ended up with an improper integral, and I can factor out the denominator as x minus 2 times x plus 1 dx. So we have a partial integral, fraction, which means I'm going to rewrite 2 over x minus 2 times x plus 1, trying to separate it in two fractions. So this is a over x minus 2 plus b over x plus 1. So pause my video and try to find a and b yourselves. So following the partial fractions, if you don't remember that, make a note and review partial fractions. There is a video about that as well. So I calculated a and b, and a is 2/3 and b is negative 2/3. So our integral now from here, I'm just going to separate it, continue it from here, is going to equal integral from 3 to infinity of 2/3 over x minus 2 dx, and then minus integral from 3 to infinity 2/3 over x plus 1. So dx. So let's calculate each of these. 2 over 3 comes in front of the integral, and then limit as n it's approaching infinity of integral from 3 to n. So because it's an improper integral, we are going to use this notation. So we change infinity to n, but we put the limit of 1 over x minus 2 dx, and the same thing, minus 2/3 limit as n it's approaching infinity of integral from 3 to n of 1 over x plus 1 dx. So this is equal to 2/3. And again, pause this video and try to do it yourself. I'm trying to save time to make more problems in one video. So when you unpause, you're going to see all the solutions. So here is all the work that we did for this problem. And because the answer is a real number, and the integral converges, then the series converges. Series converges by integral test. So please look over the work, and I hope this helps. Let's see another problem. Let's say we have sum as k equals 3 to infinity of 2k squared over k squared minus 2 minus k minus 2. So the very first step that you should try all the time is divergence test. So limit as k is approaching infinity of 2k squared over k squared minus k minus 2 Because the degree of the numerator equals the degree of the denominator, it's actually the leading coefficient over the leading coefficient. So it's 2. And so because is not equal to 0, then the series diverges by divergence test. Let's say example 4, sum as k equals to 10 to infinity of 1 over k minus 9 to the 5th. If we write out a few terms, if k equals 10, we get 1. If k equals 11, we get negative 1 over 2 to the 5th. If we get, plus, if k equals 12, we get 1 over 3 to the 5th, plus 1 over 4 to the 5th, and so on, which means we can rewrite this series as series sum as k equals 1 to infinity of 1 over k to the 5th. So now it's clearly that this is a p-series with p equals 5, and because this is greater than 1, the series converges by p-series test. Let's try example 5. Sum as k equals 10 to infinity of 100k over k factorial times k squared. So again, when this term shows up, it's this factor k factorial. The first try that you should give it should be ratio test. So ratio test. So we write out a sub k, which is exactly the term after the summation sign, and a sub k plus 1, which means everywhere you see k, you should put k plus 1. So let's do the ratio test now. R equals limit as k is approaching infinity of absolute value of a sub k plus 1 over a sub k. So this is limit as k is approaching infinity of a sub k plus 1, and because it's divided by a sub k, I'm going to put times and flip a sub k. So k factorial times k squared over 100k. So one thing that we can do is we can cancel this 100 with this one, and we can cancel, well, that's pretty much it, but I'm going to rewrite it in an easier, so I have k plus 1 at the numerator, and then k factorial, and then k squared. And at the denominator, I have k plus 1 factorial, which can be written k factorial times k plus 1, and then times k plus 1 to the second times k. So in this case, k factorial from here cancels with this one cancels with this one, and I'm left with the degree 2 of the numerator, and here it's a second order and first. So degree of the numerator is 2, and the degree of the denominator is 3. So degree 2 and then degree 3, which means when we calculate the limit of two polynomials where the numerator is less than the denominator, we end up with 0. So because this is less than 1, the series converges by ratio test.